Hey guys, welcome to module 1.3 of the Learner Space course on device physics. And today I want to talk about the most foundational concept of this semiconductor device physics, which is energy bands, right? I hope you guys enjoyed the modules before this. Without further ado, let me get into energy bands. Right. So before we are able to get into exactly what an energy band is, we need to start with energy levels. So this is probably something that everyone have seen in their 11th, 12th standard, in Bohr's model, right? Where you have, where you have hydrogen atom, which has different quantized energy levels. So before we get into what exactly this quantized energy level means, let's understand first what this energy actually measures. So the energy actually measures the interaction between the nucleus and the electrons. So the energy due to that interaction is what we are measuring when we are talking about the energy level. What exactly do you mean by the energy level then? Energy level is basically a level, a particular value of energy that is allowed to be occupied. So when we say that an energy level is quantized, what this means is that there are a set, fixed, countable number of energy values that the electron can take, which are allowed for it to take. And in Bohr's model of the atom, we actually like used like talked about this quantization with respect to angular momentum. So we said that there is a like the number of angular momentum values that you can take have to be an integer multiple of some base value, right? That was what we did in Bohr's model of the atom. So essentially, the takeaway from this slide is that energy is the interaction between the nucleus and the electron, and there are only certain values of energy that are actually allowed by atoms when you have a nucleus and an electron for that electron to take. Cool. So far we've understood that we have certain energy levels that are allowed, and not all energies can be taken by the electron. Now I want to talk about why exactly this is the case, right? Why are the energy levels quantized? And this slide, the content on this slide is slightly more, and the explanation might be slightly longer. But I don't want anybody to get overwhelmed. I'll try to explain it as simply as possible. And yes, this does involve some quantum mechanics, but we will not get into the nitty-gritties. We'll just try to get some type of intuitive explanation for this, right? So, why do I say that this involves some quantum mechanics, right? So, when you get to the scale of things like atoms and electrons, the stuff that you learn in classical mechanics no longer completely holds. Uh, what this means is that you need a new branch of physics to describe this behavior, and we call that branch of physics quantum mechanics. Now, just like you have Newton's law in classical mechanics, we have an equation in quantum mechanics that is called Schrodinger's equation. Now, what exactly this, getting into the nitty-gritties of what this equation is, or like trying to give some intuition about that, I'll get into slightly later. But what I want you to note is that this is just like Newton's law, and it cannot be derived from anywhere, and it is a fundamental truth about the universe. Uh, this equation that I've shown on the right is Schrodinger's equation. And the first fact about it is that it's an eigenvalue equation. What this means, like I'm sure all of you have probably taken some course in linear algebra, right? So eigenvalue equation is just an equation where when the operator acts on any function and scales the function by any scalar, that equation is called an eigenvalue equation. Uh, so getting into what exactly this means, right? So the operator here H is called the Hamiltonian operator, and it represents the physics of the situation, which means it represents the kinetic energy and the potential that the particle actually is in. uh, it's obviously mathematically a lot more complicated how it does it, but how I want you to think about is that H is an operator that encapsulates this physics, and specifically the kinetic energy as well as the potential that the electron is in, right? So yeah, that's on the operator. Now, as you know, for any operator in any linear algebra eigenvalue type of equation, there will only be certain values of psi such that this becomes an eigenvalue equation. And the values of psi that satisfied we will call the eigenvectors, and the values of E for which they are satisfied will be called the eigenvalues. And in this case, E is called the energy eigenvalue because it literally represents the allowed energy levels. Why this is the case is lies hidden in the interpretation of psi, right? So, what exactly is psi? It's very hard to define exactly what psi is, but you can think of it in the sense that psi is something that encapsulates the state or all the information you need about your electron. So everything you can possibly know about your electron is encapsulated in psi. So when you have only certain values of psi which are allowed to satisfy this eigenvalue equation based on the Hamiltonian operator, which defines the physical condition of the situation, that means that there are only certain states that an electron is allowed to take. And corresponding to these states or eigenvectors, you have only certain eigenvalues that the electron is allowed to take. What this means is that there are only certain values of E for which the electron, for which this equation can have a solution, and therefore, since this is the most fundamental equation of quantum mechanics, there are only certain values of the energy that the electron can take. So what I want you to gather from this is that since the Schrodinger's equation is an eigenvalue equation and it is the most fundamental equation of quantum mechanics, and there are only certain states or psi values for which you can have uh, this equation having a solution, because all eigenvalue equations have certain solution corresponding to certain eigenvectors and eigenvalues. What this means is that there are only certain values of energy that can be taken up by the electron. So this is kind of the background due to which we have energy bands, right? When Bohr came up with this atomic model, the diagram of which I've given here, where I've shown you the multiple energy levels that are allowed to be taken, he just made an assumption that let me just assume that angular momentum is quantized. But Schrodinger's equation is the true reason behind why this is the case. And yeah, that is why we have only certain energy values that are allowed to be taken, right? Again, I can give you no justification for why Schrodinger's equation is true, except to tell you that it is, and it is the one of the most fundamental truths about the universe. Let's talk a little bit more about psi, right? I told you in a very abstract sense that psi kind of represents the state of a particle, right? If this is something that satisfies you, then you can go ahead with that intuition. But if you're like unsure what exactly I mean by that, like let me be slightly more specific, right? So in quantum mechanics, what actually happens, again, this is not something I'm going to get into the exact explanation of, but what exactly happens is that you cannot tell for sure where what the position of something is. You can only tell it with some probability. So uh, when you do certain operations on psi, you realize that psi encapsulates the probability distribution function of the location of the particle. What this means is that the specific way that it encapsulates it is in fact the mod of psi square, is actually the uh, what do you call it? It is actually the probability distribution function. What this means is that psi as a function gives you the probability of finding electrons at different locations. So again, if you don't like, if any of this is confusing, that's fine. I'm just trying to give some background as to why we have energy bands. Just quickly to summarize, we have Schrodinger equation, which is an eigenvalue equation. Since it's an eigenvalue equation, only certain values of energy satisfy this equation. Since it's a fundamental truth about nature, only these values of energy are allowed to be taken by the electron. And psi, which solves the Schrodinger equation, represents the state of the particle, and it does so by representing the probability of finding a particle at a particular point, right? This is the summary and TLDR of this. If any of this is confusing to you, you can go back, watch it again, and it is going to be slightly confusing, but I just want that you take the takeaways from this slide and develop some basic intuition as to why we have energy levels, right? Cool. So now that we've understood why individual atoms have energy levels, I want to start moving towards a concept called energy bands. And the reason these bands arise is when we start trying to investigate the problem of what happens when many atoms come together. So far we only considered a single atom, means a nucleus and an electron bound by this nucleus, how it behaves and what are the energy levels. Now imagine, like, in even a few grams of any substance, you have of the order of 10 power 23 such atoms. What this means is that imagine when you get 10 power 23 such individual atoms with their own energy levels and push them together in a small area, right? This is what we're going to investigate. So what happens in this case is that the nucleus and electrons of even nearby atoms. So imagine if all your atoms are in some form of a crystal, right? So the nucleus and electrons of even the nearby atoms of a given electron start interacting with it. Uh, Obviously, the main nucleus that the electron is bound to still is the dominating factors, but these other nucleuses and electrons also have some interaction energy due to the electrical attraction or repulsion forces that they apply on each other. What this means is that since the main nucleus is still the dominating factor, the energy does not change that much, but these interactions can change the energy a little bit, causing them to deviate from their original energy up or down. And also because another way to look at this is that you have a more complicated nature of the potential distribution. And when you have a different potential distribution, you have a different Hamiltonian operator acting in your Schrodinger's equation, which will change the solutions and the eigenvalues of that equation. Bottom line is that when you bring so many of these electrons together, you're going to have your energy levels starting to move up and down, right? This is the crucial mechanism that I want to give you as to what happens when these so many atoms start coming together. Cool. So at now I want to make a claim to you that at the level of the material as a whole, when you have so many atoms coming together, it leads to the splitting of distinct energy levels into energy bands. What this means is that when you have a atom, right? You have a single atom, so you have one high energy level, one of your highest energy levels, and then your second highest energy level. We have depicted that. Now, when you bring two of these atoms together, by the mechanism we spoke about in the last slide of why the interaction between the different particles causes the energies to start changing, you get some type of splitting of this energy level, right? Now, when you continue this process of bringing more and more atoms closer and closer together, it leads to the energy levels, although they are around the same center, they start splitting more and more. uh, and it creates something like this, which is like in this they've written that type of something as a nano, that type of a substance as a nanoparticle. And when you take literally to the order of 10 raised to 23 of these, what you get in fact is what we call bands. So the statement that I want you to grasp from this is that when in atoms with their own energy levels are isolated and then they're brought together in and interact with each other, these energy levels split into energy bands. What this energy band means is that uh, like the atom can take any energy level in between this band, because there are so many different energy levels that are present there. Imagine a band of say thickness say 0.1 ev, in which you have by the way, ev is a unit of energy, it's called electron volt. 0.1 electron volt, in which you have 10 raised to 23 different energy levels. Because all these energy levels have split, it's almost as if the electron can now take any of these energy levels, whereas initially it was bound to only a single energy level. So again, bottom line of this statement is, due to these interactions, these energy levels split into energy bands. And this is like one of the most fundamental analysis that we need to do of semiconductors, which is what their bands look like and what implications this has, right? Uh, cool. Some terminology. The topmost band is called the conduction band, and the band just below that is called the valence band. Uh, I'll just like tell you a fact which we'll talk about more, but just to give you some flavor as to why we are talking about all of this. When you bring a lot of electrons together, a lot of atoms together, the electrons that are actually able to now make it in the conduction band have such high energy that they're no longer bound to any single atom, and they can actually go ahead and move freely throughout the bulk of the material. What this means is that you're actually talking about how electrons get into the conduction band. That is the question of interest now, because we know that once they are in the conduction band, they are able to move freely and conduct electricity, right? If you didn't understand this, it's completely okay. We're going to cover this in more detail in the next module. I just wanted to give a slight taste of that. Cool. So bottom line, energy levels split into energy bands. Uh, One more point that I wanted to cover is that the quantization still exists, right? I know your question might come to your mind that, oh, you had like these discrete energy levels and now how are you getting these continuous bands, right? The truth is that you aren't getting continuous bands, but because of the sheer number of atoms coming together, it becomes an almost continuous distribution. There's a typo here. I meant continuous. I've written discrete. Please note that. So it becomes an almost continuous distribution. What this means is that in a very small amount of energy, you have a lot of quantized energy states, which means that the energy is almost in a continuum of states available, right? Between 3.9 and 4 electron volts, you have of the order of 10 raised to 23 energy levels, which means basically any energy you want to take between these two values, you have a state available for that. Whereas earlier you had very clear demarcations between energy levels which you are allowed to take. Now I just want to like show you some like interesting fact or corollary of this, which is not a corollary, but like I just want to tie it back to some principle that you're probably already familiar with if you've done it in like 12th standard, which is Pauli's exclusion principle. Now, Pauli's exclusion principle tells you that no two identical fermions, fermions is just a more general word for things like electrons. So we can just read the sentence as no two identical fermions can occupy the same quantum state. This is why in like JEE chemistry or like 12th standard chemistry, when you see when you're filling the atomic orbitals, you fill only two electrons per orbital, because with like one spin up and one spin down, no other electron can occupy this quantum state, right? So now, what happens when you bring so many atoms together, all with the same energy levels? It's no longer, due to Pauli's exclusion principle, it's no longer possible for two electrons to have the exact same energy level, because then they would have the exact same quantum state, right? What this means is that when you have these electrons come together, these energy levels need to split into as many number of atoms that you're bringing together, because no two atoms can have the same energy level, because this would violate this Pauli's principle. So that's why each atomic level splits into a band of allowed energies. It is necessary to fit all the electrons without violating Pauli's rule. Finally, before moving on, I just want to remark on one last thing, which is that when you have energy level, you're talking about the energy levels of an atom, whereas when you have energy bands, you're talking about the allowed energy levels for the electrons of the material as a whole. So I want you to like note this distinction. Energy levels are the energy levels of the electron of a single atom, whereas energy bands are the allowed energy levels of all the electrons of the material as a whole. That means if I take like few grams of silicon, that few grams of silicon will have energy band corresponding to all the allowed energy states of all the electrons in this silicon, because the way we constructed it is by bringing so many individual atoms together. So this is a property of the it's a bulk property of the material as a whole, whereas energy level is a property of a single atom. That's like one last thing I wanted to remark on this. Cool. Final slide is the key takeaway and what we're going to talk about in the next module. The key takeaway for me that I want you guys to take away from this module is that the allowed energy levels split into energy bands in accordance with the quantum mechanical behavior of the interactions. What this means is that, remember I told you that when you have all these atoms and electrons very close to each other, they affect the potential energy, which then goes ahead and affects the solutions of Schrodinger's equation, which means that in accordance to the quantum mechanical behavior of the interactions, these allowed energy levels split into bands. Yeah, that's the takeaway that I want you guys to have. And finally, in the next module, we're going to actually go ahead into what the physical interpretation of energy bands are, and how this leads to mobile charge carriers like free electrons and holes, and how these are actually able to go ahead and carry current, right? So this is the next module. Hope you guys enjoyed this module and hope to see you in the next one. Bye bye.